Good morning, everyone. Welcome back. I know a lot of us were at the Progressive dinner last night, so I'll try to be a little more lively so we don't drift off after all the nice wine we had in the late night. Every morning or every week as I'm starting to think about what I'm going to say next week, I started thinking this week is going to be now I'm going to get to the fun stuff. And we do. It always keeps happening to me anyway. So hopefully this will still be fun. It's fun for me. We're going to be talking a little bit at the beginning about the different kinds of particles. We talked about the whole zoo of particles last week and the big phone book where you figure them all out. And there's hundreds and hundreds of different types. We're going to look at just a few examples now so we can reinforce the idea of what the structure of the universe really is, how these elementary particles are laid out. And then spend most of the time talking about how we actually know these things, the way that we are able to do particle physics experiments, the kinds of accelerators and colliders that we have, and then mostly what it really looks like to do an experiment, what the equipment looks like, and what the results look like, and the overall theme of how it's done. And how it's done really depends on knowing a little bit about the interactions between these things. So it starts out, you don't know anything, you just see this big mess of particles, you try to put them in some kind of an order, so we get some kind of a way to just structure it somehow, some kind of a periodic table-like thing. And then once you have that, you can start using that information to build more sophisticated detector assemblies and then learn more in a sort of a bootstrap method until we get to where we are now and it becomes fairly straightforward. So we'll see all that. So I'm going to start today by going back to the different sets of elementary particles. This is really just the categorization where we had really two major categories. One is things that have a spin of a half integer, and those are the fermions. And the other side are the ones that have whole integer spin, which are the bosons. They turn out to be different kinds of things. The bosons are the things that carry forces around, that kind of mediate the forces, or the intermediary. They carry the message back and forth of what this force is, whether I'm attracted to you or repelling, or whatever it is. And the fermions are the stuff, for the most part. In particular, the quarks, the hadrons that feel a strong force there. But the other difference, just to keep in mind, is that the spin makes, is that things with spin a half follow what's called Fermi statistics. That's where two things that are identical can't be in the same place at the same time, more or less. And that's why you have energy levels in atoms or in nuclei or any of these things where I have a certain number of electrons can be in a certain place, and then I get pushed up into higher levels and pushed back down, and all the stuff that we talked about the first couple of weeks is because we have half integer spin in those kinds of particles. So an energy level can fill up, and then I can't add any more to it because it's already full. That concept of something filling up, not being able to have two things that are the same in the same place, that's the fermion story. That's where that applies to. Bosons, it does not apply to. I can have as many bosons that are identical packed into the same spot as I want, and that's why lasers work. Because lasers use photons, right, light particles, and the whole point of a laser, the whole way a laser works is by aligning all those in the same, the waves are all lined up, everything is not synchronized, they're all together in lockstep, and that's possible because they are bosons. There's other things that happen in other branches of physics that are a consequence of these two differences, but that's really where the chart is split up. That's why spin matters. When we get to the fermions, there's really two categories, and the whole structure is really based on which of the forces different particles feel. So there's three forces that we talk about. Gravity we don't talk about because it's too weak and you need too much stuff for it. But aside from gravity, you have three forces. The electromagnetic force, that's what we're all used to. That's what you feel and interact with in daily life. Those are the plus and minus charges that either attract or repel each other. You have the strong nuclear force that we talked a lot about the last couple of weeks. And then you have the weak nuclear force. And which particles feel which force is essentially how they're categorized, how they're broken down. So the leptons have no strong force, they're just weak, and some of them are electromagnetic, some of them are not. And then the quarks do feel the strong force, and then the quarks can be grouped together because of that strong force to make hadrons. You can't have a quark by itself, it has to be with something else. And the hadrons fall into two categories, one where you have three quarks and one where you have two quarks. And the reason it's broken down that way is because of the nature of the strong force. So I had on the board, I had two boards, I had this on the board in a slightly different way. I'm going to leave this up here for a little while we talk, just so we can keep in mind what's going on. The quarks are over here, I have the leptons over here. Again, the difference is these guys feel the strong force, and these guys don't. They all feel the weak force, and the ones with charge feel the electromagnetic force, which is everything except for these neutrinos. Again, they're organized in pairs. I have up and down is one pair. Charm and strange is the second pair, and top and bottom is the third pair. These are called generations. And I have, just like I have 3 generations of quarks, I have 3 generations of leptons. There's no intrinsic reason why that seems like it should be true, but we really wanted it to be true. You may recall from last week that we spent a lot of time searching for other particles as soon as we figure out there's an imbalance either between whether or not I have pairs here. For a while I had up, down, and strange. I didn't have charm. We hadn't discovered it yet. Somebody said this, we really ought to have something that balances that out, which is why it was called charm when we found it. And then top and bottom, it was funny with that is we had the tau and tau neutrino, and with the top and bottom quarks, everybody really, really wanted them, so we all just decided we're going to believe they're there. And eventually we found the top quark, which was the last one. It took quite some time, and it was one of the least surprising announcements in all of particle physics. I mean, huge machines were built, people worked careers on finding this thing, and we found it and said, thank goodness, that's pretty much it. But nobody was really surprised anyway, because we like this symmetry, we like this structure. And then, what I have then over here, these are the things that carry these forces around. So the gluons carry the strong force, which is expressed in color. That's what we call the charge of the strong force. And then the photon is electromagnetic, which applies to all of these things, but not the neutrinos, they're not charged. And then the weak force, which we'll talk a little bit more about, is the W's and Z's, which applies to everything. These things, the different labels, I'll call them flavors. So I have 3 generations, and each of these are the 6 flavors of quarks. The flavors will count.
George, the photon is affected by the electromagnetic force, and I have the impression that light as a photon shouldn't. Can you just give me a little more information?
The photon, it's not that it's affected by the electromagnetic force, it does not have charge, so it is the carrier of the electromagnetic force. So if I have 2 charges, the way to think of it is if I have 2 charges that are here, there are photons being exchanged between them. And that's what mediates the force. That's what creates that exchange creates the force, whether it's attractive or repulsive there.
Could you distinguish between using the word force and mediate? Because they seem to have a kind of a different meaning.
They do have a different meaning. Well, the reason is that if you think of it in conventional terms, I think of 2 charges, and I'm going to throw something back and forth between them, that's going to push them apart. And how can I throw something back and forth and have it pulled together? That's why it's a fundamental limitation of using just regular English language to be able to talk without the mathematics, is you have to understand that they're not really throwing a football back and forth and pushing. These particles are just what creates, it's how the force is expressed. It's really a field that's doing this, and that interaction between what's a field versus what the particles are as ripples in the field is something that I don't really want to try to convey accurately. For the most part, what's important in terms of understanding the phenomenology of these things, which is to say how everything interacts and why everything behaves the way it does, is just that there's an exchange. And if you think of them, rather than throwing the football, you think of them as messengers that carry the information of what the force is between, that'll give you a reasonably accurate intuition for what's happening. So what I want to talk about with the strong force a little bit is how the color charge of the strong force works. So I got a head start here, and we talked about last week, I take these things, the quarks in particular, I can group them up in different ways, and I can make hundreds of different particles. But I'm just going to look at, I have on the board the particles that we'll talk about today, specific examples here, because they're the most common things. On the top I have a proton and a neutron, which are that's what matter is made out of. That's the nucleus of the atom. The regular stuff is protons and neutrons with the electrons on the outside. So normal matter is really what's above this line. I've got my protons, my neutrons, my electron. I also have neutrinos, which we don't have a lot of daily experience with because they fly right through you and you don't notice them. They're very important for the interactions that happen. They are actually a part of daily life. They're not an obscure particle, but they don't have any real impact on us. We don't do anything with them. But they're still above that line of normal matter. And then the proton and the neutron are each made up of the quarks, and the quarks they're made up out of, conceptually, are these two ups and a down for the proton, and an up and two downs for the neutron. Remember also that with each of these, every single one has an antiparticle partner, which is exactly the same except opposite. Opposite charge, opposite everything, but otherwise it's really the same particle. It's kind of a mirror image particle with a different charge. So I can group 3 of these together to make a baryon, or I can group 2 of them together to make a meson. If I group 2 of them together, these are things now that are they're around all the time. They're streaming through your body right now, but coming from space, from all kinds of places. But you don't normally think of interacting with them. You don't consider these things normal matter, even though they're made out of the same stuff. So the ones that are here, that are relevant to us, are the ones that are easy to make, the ones that are made of an up and a down and a strange, kind of the lightest, easiest things to have. So those are pions. There's a couple different kinds. I drew a pi plus, which is an up and an anti-down. I can also have a pi minus, which would be an anti-up and a down. Pi 0, 2 ups. It's actually partly 2 ups and partly 2 downs, or 1 up, anti-up, 1 down, anti-down. And then kaons, which is the first particle we have, the latest particle we have that has strangeness to it, that has a strange quark. Remember when they first found the kaons, they behaved strangely, and so they assigned a property to the kaon called strangeness, and this thing just has the strangeness property. Later we found the strange quark, and so the reason it has the strangeness property is because it has the strange quark, and because that, in order to make that change from the strange quark to something else, only the weak force can do that. The strong force can't do that, and that was strange. So the rule for the strong force is you have color is your charge. So instead of having a plus and a minus, I have a red, I have a green, and I have a blue. And whereas the plus and minus attract if they're opposite and repel if they're the same, with color, I have to have something colorless. I can't have an individual item that has color. I can get to colorlessness 2 ways. One is by combining one of each, a red, green, and blue, and that makes it colorless. Or by having a red and an anti-red, or green, anti-green, blue, anti-blue pair. And the color and the anti-color then cancel out, and from a distance it also looks colorless. That is why I have 2 kinds of composite particles I can make. I can make a proton with 3, because one will be red, one's green, one's blue. I can make a particle with 2, because one is red, the other will be anti-red or green, anti-green. That's also why these are either going to be all particles, not antiparticles, and this will be 1 particle, 1 antiparticle, 1 quark, 1 antiquark. So it's quark, 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 or I can make an antiproton, which would be anti-U, anti-U, anti-red. Anti-up, anti-up, anti-down would be an antiproton. But that's why this is the whole family of what I can make. And then all the rest of the particles are just different ways to combine these things, or different ways to get to excited states. So how does the strong force actually work? What does it do? Let's take the proton. So I have my proton that's going to be an up, and a down. And what the strong force does, I have to be colorless, so these things have to stay together. But what if I go in there and I try to grab one, and I yank it out? What will happen is, I take this up quark, let's say, and I start moving it over here. They're still fairly close together, but I'm pulling it apart. I'm pulling this particle apart. As I pull it apart, think of there being like rubber bands that are stretched between here. And it's hard to pull it apart because the strong force needs to keep them together to be colorless. And as I pull them apart, that rubber band is stretching tighter and tighter and tighter and tighter. It really doesn't want them to separate. At some point, what happens is I'm far enough apart, and the strong force, remember the strong force is a local force. It only applies over a narrow range of distance. Even though I'm really stretching out that rubber band, I get to a point where the strong force breaks. The rubber band breaks, it's too far apart, it snaps. What happens when it snaps? It looks like, well, now I would have something that is colored, that is away from anything else. It's by itself. I can't have that. So, what the universe does is it creates out of nowhere a pair of particles, which you're allowed to do. But you have to do them in pairs. It has to be a particle and an antiparticle that I create at the same time. And I can't create them, of course, out of absolutely nothing. I have to create them out of some kind of an energy. The energy that creates this thing, this pair of particles, comes from whatever energy it was that was stretching in the first place. I can't just stretch it for free. So all the energy of pulling it goes into popping this pair of particle-antiparticle pair, quark-antiquark pair, pops out of nowhere and shows up. And then when the rubber band breaks, these snap. You get a D over there, it's a dud, and an UD over here. And now I have two particles. This one, the order of these things doesn't matter, is a neutron. This one, my up-down bar, is a pi plus. So what I've done is I've now taken a proton, and I've made my proton go into a neutron and a pi plus. That interaction is what just happened here. I did that by starting with my proton and trying to grab a quark out. But instead of, well, I'm not really going in, picking up and pulling it, the way I really do it is by punching it. I come in here with something really fast and small and hard, and I smack this thing, and I hope that I hit one. And when I hit one, it kicks out with enough force that this is able to happen. And that's one of the basic fundamental ways you study things. That is called deep inelastic scattering, and that it brings us to deep inelastic scattering. That's right here. Jerome Friedman, in fairly recently, 1990. The reason it's called deep inelastic scattering, elastic scattering is billiard balls. Things just bounce off. Inelastic scattering is where some energy, something gets broken in the process, right? So if you crash your car into a brick wall, that's inelastic scattering. If it's elastic, it's if your car is made out of a rubber ball. Bumper cars are elastic, real cars are inelastic. Deep means I'm going with enough force that I'm getting inside the thing. And that's what we did here. That's how we took some kind of energy, smashed something into here, and we're able to pop these two things out. And that's the way the strong force works. Question? Somewhere?
Yeah, I wanted to ask you, I mean, you can rewrite it and put a gluon in between the original up,
Right.
right? And you are saying it, so I imagine that as you are moving it out, right,
Mm-hmm.
you're coming outside the range of effectiveness
Right.
of the strong force.
Yes.
Now, what is the other principle which you invoke now in order to create two of them?
Well, I can always.
Is the principle of conservation of energy?
I can always, if I have the energy to create something, I'm always free to create anything that I have, anything that I want. So if I go down to, each of these things has a certain mass. If I have enough energy that is more than the mass that I need to create a pair of things, then I can create them. I'm allowed to do so, and it will happen on some statistical basis. And that's, so if I have, for example, a photon that comes in, if that photon has a certain amount of energy, I can create two electron type things. So I'll have a positron and an electron, which is an electron and anti-electron. Again, with electrons, the notation is funny. This should be an E bar. You can follow the convention of everything else, but we don't. We just call it a positron. That's the same thing. That's just historical reasons. Because the positron was discovered 32 or something, a long time ago, before we had the rest of this formalism here.
But the photon itself doesn't have mass, but the
Mass-
electron and the positron do have mass.
Mass and energy are not distinct things. They are the same thing. How you move back and forth from mass to energy, energy to mass, it's all one thing. Yeah.
That chart that you just had up on the screen, is that part of the periodic chart?
That's not part of the periodic table. It's sort of the equivalent for fundamental particles. This chart, and if I take this and I take an exact copy, it's all the antiparticles. These are the fundamental particles in the universe. This is what everything comes down to. This is made out of this. These are not made out of anything. Anything that can be built or made or anything is all just made out of these. Yep.
So you were saying that basically protons, neutrons are made of the quarks, leptons, fermions, and bosons. What's the role of the particles of the phi and the k's compared to those ones? Why they're not in that table?
In this table here?
Yeah?
Well, each of these things, the protons, neutrons, pions, and Ks, are all just made out of quarks.
Okay, so the elemental particles are those in that table.
Right.
Then all together make the p's, n's,
Right.
pi's, and the k's.
The P's, N's, Pi's, K's, all these things are just made up
Now,
of these
in a
parts.
very elemental understanding, you said initially protons, neutrons,
Right.
and the ones below, where are they?
The protons, the reason I have the line here is that these are the things that normal stuff is made out of. Every object we interact with, everything we have, regular material, is all made out of protons, neutrons, electrons, neutrinos. Stable things. But it's everything that's a thing that you're interacting with, you touch. Stuff is made out of this. These are particles, they are real, they are round, but they're not stable. I mean, actually the neutron isn't even stable, it only lives 15 minutes. But if it's free. But these other things are more ephemeral and don't collect into making atoms and those kinds of things.
I'm assuming the two up course, the up and the anti-up,
Mhm.
electromagnetism is keeping them from coming actually together and blowing themselves up in the pion not or pion zero. Like something's
Yes.
obviously keeping them from blowing up.
Right, well, what really happens is they annihilate and they get created again. And they're annihilating and creating continuously. So I'll have the up, anti-up, they'll annihilate into a gluon, and then they'll come back into another up, anti-up, or maybe a down, anti-down, or anything else. And that's going on continuously, which actually brings me to the next point I want to make, which is that we've talked about the fundamental building blocks of proton or neutron. So I have a proton, which I keep drawing as up and an up and a down in a circle, which you think of as being these three balls that sit there inside the one bigger ball. And they're held together with gluons, right, which is what keeps them from, the fact that these have the same charge keeps them from flying apart, keeps this thing together. It's a nice conceptual picture, and it helps us figure out how to make things out of these particles. But it's not what actually goes on inside one of the protons. What actually goes on inside a proton, a neutron looks more like this. It is a gigantic mess of about a bazillion, maybe a bazillion and a half of quarks and antiquarks of all kinds, mostly up and down, but then there's some strange ones in there as well. And then a bunch of gluons that are flying around as well. And all these things are constantly crashing into each other. The matter and antimatter particles collide, annihilate, turn into energy. That energy turns back into more particles. And it's like a bubbling, boiling mess of stuff that's going on in there constantly. It's not just this simple picture. And we do distinguish between the three quarks that we've got here and the big soup by calling these things the valence quarks, and by calling those things, the rest of it, the C quarks. And it turns out that if I take the huge mess of stuff that's in there will be, if it's a proton, I'll have an excess of two ups and a down. Everything else cancels out. If I took every bar and every U and U bar pair here, and I cross them off, and I cross the D and the D bars off, and I'm done, and everything is collided with everything else, and I'll be left with those three valence quarks. All the C quarks would cancel out. The key is that the valence quarks and C quarks, they're not actually separate, different, distinct things. I can't say which one of the quarks in here is a valence quark. Not because I don't know, but because it doesn't have meaning. Right? The excess is what we call the valence quarks. We use them as a bookkeeping tool. But the reality is there's just this huge soup of a mess that's in there.
Yeah, if you're saying that all of them all constantly collide and doing the reaction, whatever they do, and material to material, certain excess energy, that should be always visible and always like seeing the energy excess somewhere. So why we have cold material and so on, because that means that there are no energy inside.
This is all confined within the body of the proton.
Mm-hmm.
So you don't get, the only thing that potentially leaks out is the residual strong force, which is what is able to hold the neutrons and protons together inside the nucleus.
Mm-hmm.
But the motion that's in here is not it's not a thermal motion. It doesn't come out that way. With the composite particles, you do get thermal type motions. But within the individual protons and neutrons, it's all held within that boundary. And part of that is just because the range of the strong force is so small. What does happen though, and this is a significant thing, why do I think, if this is what it really is, right, how do I know that? And that comes back to the question of deep inelastic scattering. So what I can do is I can shoot a particle into here to collide and hope that I kick something out. And I can kick out one of these quarks. And by doing so, I can measure how much mass the quark has. I can measure what the spin of the quark would be. And I come up with a couple of funny things. If I look at the masses of these quarks, the mass of a quark is about, it's about 5 MeV. But 5 is the mass. If I look at a proton has a mass of about 1,000, 938. But it's 938. So I have 3 things that weigh about 5. I add the 3 5s together and I come up with 938. There's 3 different types of energy that are in here. Remember, energy and mass are the same thing. One is the mass of the constituent particles. If I talk about most things we have, like the solar system, that's a really big part of how much energy there is the mass of all the planets. In the case of protons, neutrons, that is not where the energy is. It's not in the mass of the constituent pieces. There is a big piece of it that's in the motion, of the fact that these things aren't sitting there, they're zooming around constantly, very quickly. So there's a lot of energy in that. That's where much of the mass comes from, and the rest of the mass comes from the confinement, the fact that they're stuck together, the fact that if I broke it apart, I would get energy out. There's energy in there of that confinement energy, which is also true in the solar system, for example. If I have something orbiting, if the moon crashes into the Earth, that would be a big explosion. Not a big bang, but it would be a big explosion. Kill the dinosaurs, for example. That energy, that's that confinement energy. That's the energy of being in a system where I have a force between those things. So that also accounts for a substantial portion of the mass. Yeah.
Can you accidentally bump out a strange when you do that experiment? When you try and bump out up and accidentally hit a strange?
Sure. You would make, in that case, the cation, which is a D and an S. So I can have an SS bar that would come out, and I can make other things. I have to have enough energy added to be able to do that for a strange. Because the strange particle now, the strange quark is much heavier than the up and the down quark, so I need more energy to do that. So if I'm in a low energy accelerator where things are just barely able to get in there, I won't make any of them. As I turn the energy up, and I'm basically hitting harder, then I have more energy. Then I can make strange particles, and I can make charm particles. That's why it took forever to find the top quark, because it's big and heavy. It's not big. It's heavy. It's drawn as being big. And it takes a higher energy accelerator to get there.
So couldn't you actually predict what you're going to kick out depending on the energy you shoot in?
Yes. Well, you can predict you're going to kick not on a case-by-case basis, on a statistical basis. So if I keep kicking, I'll know 10% of them are going to be this and 30% of them are going to be that. You predict. Barbara.
The fact that you've got, you said you boil it down after everything cancels everything out, you've got left and up and up and down.
Right.
Is that what makes the proton have a positive charge?
Yes. That's right. That's the charge and the spin are both, the spin sort of, conceptually the charge and the spin are both attributable to that. So I'll have a plus 2/3 minus a third here. And I have a 2/3 plus 2/3 minus a third is a charge of 1. So that's what I get for the proton. In this case, I've got plus 2/3 minus a third minus a third. That's why the neutron is neutral. In these cases, that's why I can have a pi plus or a pi 0, just by what the constituent quarks are. So that's the mass question, which is fairly easy to understand because we have those 3 sources of mass that we're familiar with. What was more problematic until, I don't know, more or less the end of the time that I was in grad school, was called the spin crisis. It has other more pedestrian names, but that's where if I go in and I actually measure the spins of each of these things inside, that does not really add up. If I have conceptually again with the 3 quarks, I should have, and I know that the up quark has a spin of a plus a half. I've got plus a half, minus a half. I should have a spin of a half. So my bookkeeping, that works. When I go and actually measure, okay, what's the spin of this quark, I add them together, I don't get enough spin. And that's again because of the boiling sea of stuff that's in there. You will almost always see this picture if you see, okay, what's in a proton? So a proton is going to be 2 ups and a down. And again, it's bookkeeping, it helps us do things, but this is fine for a theoretical picture.